Hello everyone and welcome to the Bangalore Theory Seminar Series. Today we have Dheeraj Nagaraj as our speaker. Dheeraj is currently working as a research scientist at Google AI Bangalore. His research interests include design of learning algorithms for data with temporal dependence, theory of neural networks, random graphs, and stochastic approximation algorithms. Before joining Google AI, he obtained his PhD from MIT under the supervision of Professor Guy Bressler. Today he'll be talking about utilizing the CLT structure in stochastic approximation of sampling algorithm. So without further delay, I hand it over to Dheeraj.
Thanks very much. So yeah, like Srinivas said, I'll be talking about CLT analysis of stochastic gradient based sampling. So this is joint work with Aniket Das, who's a pre-doc at Google, and Anant Raj, who's a postdoc in INRIA and UIUC. Okay, so let's get started. What we'll be focusing on roughly is a sampling problem in a continuous domain. So you have a function f, let's say it's positive and from Rd to R, and we have a probability density that is pi star of x is proportional to e to the minus f of x. Pi is sampling from this Rd. In Rd, there's a curse of dimensionality. You can't approximate partition function. There are too many balls you need to approximate. So you need some nice sampling algorithm from this for various kinds of tasks. Okay, so for instance, if you want to do generative models or Bayesian inference, you want to sample from potentials like this. In statistical physics, of course, where it is everything is inspired from, this is a fundamental problem. It's called a Gibbs measure, and f is called a Hamiltonian. So in theoretical CS, it comes up in convex bodies and volume computations and so on. And this is also a fundamental problem there. And also these days in differential privacy, that is, if you learn using exponential mechanism, it involves sampling from such a distribution, and it is assured to be private, differentially private.
This is support of phi. Phi is bounded in some way.
It's not bounded, it's unbounded.
When you say it's sampled from.
It's a probability density.
But volume computation, for example, entails looking at
right, yes. So in that case, what you make is make f infinity outside a bounded domain. Okay. But we won't be considering that in this unbounded.
Is that, like, my question is whether that makes the problem simpler?
It uses a different kind of techniques. Like for instance, the whole work by Kernel Lower Simonovitz, that's mostly in the convex body. They use projections and hit and run walks, etc. But correct. This is also a Markov chain, but you don't do projections into smaller bodies, bounded bodies. So yeah, so we will be approaching this more from.
The answer is like they are incomparable.
There are of course similarities, but they're in a sense incomparable. We approach it from a different perspective. This is more from the Bayesian inference generative model perspective. So, okay, so let's look at the most primary algorithm people use for this in continuous domains. It's called Langevin Monte Carlo. Okay, what is this? Okay, so you have iterates xk plus 1 is equal to xk minus, you decide along the gradient of f of x, and then you add a very large Gaussian noise, right? So it's gradient descent plus very large Gaussian noise. So okay, we return xk for some large x. So here's a cartoon. You have this Brownian motion, and this is the gradients, and it's doing a random walk, but also descending along the gradient. One thing to observe is that this, when eta is small, the step size, square root eta is much larger than eta. So the amount of noise you're adding is much larger than the signal. Right? So why is that? Because it is the Euler discretization of Langevin dynamics, right? Which is a stochastic differential equation, right, of this sort. So here the Brownian motion locally, when t to t plus epsilon, it grows as a square root epsilon, and this drift function just grows as epsilon. So if you want to discretize stochastic differential equations, this is how you discretize it. Okay. So sampling under log concavity, that is when f of x is convex. For instance, this also because it's a discretization of a stochastic differential equation, right? If you take a Brownian motion, okay, from vt at time t, it's of the order square t, right? It's fluctuates typical value, but the value of this drift, grad f of x t dt, integral of that is of the order t, right? When t is small, the noise dominates, but on large t's, it just gets cancelled out, right? So when you want to do a local update, you may add a very large noise, and hopefully over the course of time, it will get cancelled out. And give you an example. That's the. Okay, so yeah, this is more closer to what you are referring to in the TCS community. Here, basically, you take it to be an indicator function where it is 0 inside a body and infinity outside a convex body, right? But okay, this is not the way to sample from that. There are other ways to do that, but yeah, so it fits in the framework in some sense.
I mean, there's also this like meta equivalences between sampling, optimization, and integration. So
Yeah.
does that show up, or you're actually working with this? The intent is to start with a like one of these dynamics and analyze that.
Correct. So yeah, there is of course equivalence. Like for instance, Bayesian inference can be also seen as an optimization, and this can also be seen as an optimization in the space of measures and etc. But so we have, let's assume that we have done all that theory and we know why we are sampling, because we want to do one of the important tasks, and so we have reduced that to sampling. And how do we sample? That's where the level of abstraction we're working. Okay. So you have this stochastic differential equation, and you discretize it into this Langevin Monte Carlo, which you can actually run on a computer. Okay, so what kind of distributions are easy to sample and what kind of distributions are hard? The classical answer is, okay, if f is convex, this is like a convex gradient descent plus large noise. So the distribution looks like this nice Gaussian. It's log concave, it's easy to sample, it has all the nice properties, and you can write all the nice functional inequalities and so on, and this is easy to sample. But functions like this, which are not log concave, can be very hard to sample. For instance, if you end up in the small mode, right, there's a bottleneck here, and it will take a very long time to, if you start out here, to go here with where there's a majority of probability. So this kind of probability distributions are hard to sample for this algorithm, right? If you are doing local, it's kind of like a local minima in the space of probability distributions, right? Okay. However, we can actually push it further than log concave and not log concave, right? This one. So, like I said, if you are in the small part, right, there's a bottleneck here. So what happens is it does not even sense this existence of this. This will just look at it and say, oh, this is just a Gaussian here. I'll just stay here. It can't even sense that there is a huge peak outside it. So the algorithm, because it's a local update, and it will take a very long time for Brownian motion to be large enough that it pushes it into that domain.
Just to be pedantic, the curves here are of pi star x.
Yeah, per pi star x. Yeah.
And then what you're saying is that these local like, gradient steps would not, and this is kind of like gradient descent getting stuck for non-convex.
Correct. Exactly. It's exactly.
Is the noise that you had helped in these cases?
Yeah. So okay. So Brownian noise is very, very small, right? It's very, very well concentrated near zero. So if you want to go like into large deviations regime, it takes exponentially long. If you want to go a long distance with just by pure chance, the Gaussian will skip there. However, if you had jump noises and heavy tail noise, you might have a better probability of reaching them.
So noise does not help with the
Right, exactly.
You're not assuming any start condition.
You can, okay, so how this works is, okay, you consider some initial condition so that, okay, there is an initial condition where it doesn't work. But here, for every initial condition, it mixes. So that's the kind of guarantee. But you can also move beyond this worst case analysis, but that's a different line of work altogether. So yeah, okay. So you can actually go beyond this dichotomy of log concave and not log concave. That is sampling with isoperimetric conditions. Okay. So there is something called logarithmic Sobolev inequality and Poincare inequality, which are functional inequalities which come out of Bakry-Emery theory. And this is a very rich theory which combines geometry and measure theory and PDEs. Okay. So what this says is that, okay, log concave is always easily sampleable, but this kind of thing which is approximately unimodal, but there's also some pits here, but they're very small. So they're bounded amount of pits. This also satisfies some, this is not log concave, right? But this is actually satisfies something called the logarithmic Sobolev inequality, right? And this is actually much different from this. There is a clear bottleneck here, but there is no clear bottleneck here. Here you would expect that it senses everything around it, right? So actually you can move beyond this log concave sampling and sample with logarithmic Sobolev inequality. To give you a high-level intuition as to what this means concentration of measure, right? So Gaussians, we know, measure concentrates. All Lipschitz functions of Gaussians concentrate. Similarly, if it satisfies a logarithmic Sobolev inequality, all Lipschitz function of this random variable concentrate. Very well. So that is what it roughly means. But for now, we'll use this intuitive picture that, okay, this is stable to perturbations. If you perturb the density by a little bit, even if it is not log concave, it will still satisfy a LSI.
In this case, the noise will get you out of it.
Yes, in this case, the noise will get you out of this. But it's a bit more mysterious how it does that. Like you have to go into more functional analytic viewpoint, PDE viewpoint.
But you are, like in all these three cases, you are confining yourself to like the dynamics that you propose.
Right.
Convergence of that.
Right, yeah, Langevin, because it is, we are trying to restrict ourselves to this Langevin dynamics type algorithms because of the applications we are having. But of course, we can try to analyze Hamilton Monte Carlo and it's one of the future works. Even this time variation gradient design, but we will just stick to this. Okay, so the recent works, like especially by Bibisono and Mpala, Balasubramanian et al., and has focused on proving convergence of Langevin Monte Carlo for under isoperimetric conditions, that is logarithmic superlevel inequalities, Poincare
F is say not like that is not say log concave but satisfies superlative. I'm just trying to understand like a motivating application for this.
right. Okay. So, if, like I said, it is this one is more stable to perturbations, and we want to actually tie it to back-end theory, which works with log superlevel inequalities in general, not just log concavity. We don't want to impose that.
So, like, say in the context of volume estimation isn't the best of context, but is there like a say in the Gibbs sampling, the statistical physics world, what is a nice application to keep in mind?
Right. So I'm approaching this from the viewpoint of optimization itself. Like computer scientists care more about optimization, but this actually has more better properties of escaping shallow local minima. So if there are like if you do empirical risk minimization or something, there are a lot of shallow local minima, and you want to be able to escape those. And this gives you a tractable theory to do that. And there's a lot of theories which show that okay, deep learning might approximate a Langevin descent rather than a stochastic gradient descent. Right, so this also models how we get out of these very shallow local minima.
So I'm guessing K there is the small k, right? Like the amount of time taken. And what is D?
Yeah, this one. So this is capital K. So if you output the iterated capital K, okay. D is the dimension, latent dimension. So we have polynomial dependence on that.
Irrespective of the starting.
Okay, you need a warm start, that is, it should have a finite KL to the starting point, but it is very easy to get that by using an appropriate Gaussian initialization. It's not a big deal. Okay, so sorry about the animation. So in several large-scale problems, we have grad f to be an expectation of other components. So the problem with running LMC is that okay, at each step you are spending O of ND computation per iteration, which is not something you want to do in the modern data science. There might be hundreds of thousands of n might be hundreds of thousands, d might be hundreds, and each iteration is very very expensive. You don't want to do this. Okay, the solution, just like in deep learning, is to use stochastic gradients. That is, you want to do stochastic gradient Langevin dynamics, which was proposed in Belling and Tay in 2011. This actually works magically well, much better than stochastic gradient descent, but it's not very well analyzed. Okay, so let's say here what we do is instead of using capital grad f of xk, what we do is we draw a random batch of b samples, okay, and compute the gradients there and replace this by this empirical average instead of the grad capital F. Right, and this hopefully will approximate it well enough in long enough duration of time, and we'll reach the global minimum. And of course, this has been studied theoretically by Zhu et al. And we also want to study this kind of a batch approximation. So we saw this as the stochastic approximation. Okay. So the questions we want to ask is, what are the conditions for this to work? Right? When can we expect it to give us a faithful representation of the target distribution? And another question is, how should we pick the batch size B? Can I pick it? Should it be polynomial in D? Should it be logarithmic in D? The constant step size enough? So these are the kind of questions we want to ask. What is the best possible computational complexity? What is the oracle complexity of this? How many times should I query grad fi of x so that I can get a sample? If I run Langevin Monte Carlo, it is nd over epsilon squared. Right? Can I remove the factor of n from it and make it purely dependent on d? So that is a kind of question. Okay. So this is like I said, this is not just restricted to Langevin paper. For instance, let me very briefly introduce you to aggregation diffusion equations and interacting particle dynamics. These are also important sampling optimization and simulation algorithms for multi-particle systems. I'm sorry if it's confusing, but this won't be very important for the rest of the talk. Right? So there are n particles, I equals 1 to n. So they evolve by interacting with other particles. Ith particle at time k plus 1 actually descends in the direction gki, plus it has some Brownian noise, square root eta epsilon ki, and it interacts with other particles through this interaction potential. Yeah.
Sorry if this is already been explained, but typically we look at convergence into an epsilon ball.
Yeah.
But here we are looking at convergence into KL being less than epsilon.
Right. It's an epsilon ball in the space of measures. This distribution. Right. Okay. So you have these interactions. Okay, so the problem here is that you have to account for interaction of every particle with every other particle. So it's O of n square d time algorithm, and you don't want to do this. So you can again use random batches here. You don't have to consider interaction of every particle with every other particle. You choose a random batch of B particles and consider the interaction of particle I with this random batch of particles, and this magically improves the sample complexity, per step complexity to O of n dd. And this is whatever I discuss here can be extended to this scenario as well in a quite straightforward manner.
Like who is hiding some Lipschitz term?
No, okay. So this per step complexity is the same, right? It's you just compute a function.
So like my point is that imagine that like your particle systems like the anti-ferromagnetic one where there's a unique particle that really distinguishes your spin.
Right. Yeah.
Then I mean, till you look at the entire, till B is in fact all the so you will miss it with high probability.
Right. Under certain conditions, this might work. So there are certain potentials, right, which physicists use. Right. There, this kind of thing makes sense.
Which is like a Lipschitz condition.
Lipschitz condition, yeah. But there are also singular potentials like Coulomb potential, etc., which I also look at, which is actually infinity at zero. There, if because it's in 2 or 3 dimensions, you can keep track of things which are very close to your particle and add them almost surely, and things which matter a little less, you can use the random batch. So that's also possible, but in low dimensions. Anyway, so this was a segue to show that okay, this is not just restricted to Langevin descent. Wherever you have this gradient and over a population, you can just replace it by a smaller batch. Okay. So now let's get back to SDLD. Okay, so let's see how we can approach this problem. And let's do a signal plus noise decomposition. Right. So this is my SDLD. So there is a signal grad of xk, and there is a noise because I use the random batch to approximate this. Okay, so the noise can be written as this stochastic batch stochastic gradient minus whatever I should have actually used. Okay, so the signal is grad of xk. Okay, so notice that nk is the average of zero mean conditionally IID random variables. So conditioned on xk, they are zero mean and they have IID distribution. What does the central limit theorem tell us? Up to some rescaling by square root b, this law of nk given xk will be very close to a Gaussian, irrespective of what xk is, irrespective of what this distribution is. It will, so by central limit theorem, as long as the second moment exists, this will look like a Gaussian. Okay, so we can say, okay, so we know that this Gaussian noise, which you are adding, the diffusion term is exactly Gaussian of the order square root 2 eta. And this is Gaussian of the order eta over b. So you are adding a small Gaussian, extra additional Gaussian noise to a very large Gaussian noise. So this approximately can be written as this. So this is the additional noise which was introduced by our random batch, which can be absorbed into the Brownian motion like this. So this is the intuition we go with. So this is what I mean by utilizing the CLT structure. So you make this approximation. So So what we want to do is make this connection more precise, quantitative, using CLTs, and then analyze this HCLT. So we will write a few non-asymptotic CLTs and gives a state-of-the-art guarantees for convergence and batch size in terms of the conditions under which they can converge and what is the sample complexity or computational complexity. And we will also use these. Yeah, go ahead.
So you might use something like this, the martingale.
Not really. We work more with data processing inequalities and EBIs. But in some sense, there is a martingale argument. There is filtration for sure. So conditionally, there is a CLT approximation. Not explicit. Yeah. Okay. So the next question we ask is, okay, we analyze this algorithm. Can we do better? Does it suggest a new algorithm which does better? Yeah. We also actually design covariance direction, which is designed to do better by cancelling this noise out in a cheap and efficient way.
Like to apply central limit theorem, they do need the batch size to be at least some. That implicitly imposes some.
You can get a Bayesian type result, like you get, yeah. So that's the thing. That's the RTF. So you have to get a very precise dependence on the P,
Right.
and then you can pick whatever you want. So yeah, so again, I've repeated the computation, and I showed that SGLD will actually approximately equal to this in distribution. So let me tell you how to introduce covariance direction. Okay, this is basically LMC with slightly higher noise.
Wondering, like, let's say you actually knew this.
Yeah.
This, like the sampling, the noise is in some sense under your control. You're the one who's sampling, so.
Correct.
You can probably tailor-make it to a non-asymptotic version. Just trying to appreciate the significance of adding Gaussian noise versus a noise that's a bit tailor-made for.
No, this is a random batch, so no matter what noise you have, it will look like a Gaussian.
But it's a random batch because you decided for it to be.
Yeah, and it's also used in practice, so that's the inspiration.
Is there any optimization to be done over B?
Yes, there is an optimization.
So I mean, you can tailor make B to be. So you're optimizing on one side convergence time and computation.
Right. Yeah. So no, it's more like a plateau, right? If you increase B over a certain thing, it won't give you any benefits. So, but yeah, in future work, I'm working on things where you can actually go much beyond much larger batches and it will still help you. So, but yeah, future work. Okay. So we will actually rescale the Brownian motion to correct for this. We expect to add a Brownian noise, a Gaussian noise of certain covariance. We estimate the covariance and just subtract that much Gaussian noise. How do we do this? So it's called covariance correction. You take an additional random batch, okay, and estimate this covariance sigma of xk. You just estimate it by sigma hat of xk using an additional random batch. Okay, and then what you get is something like this. So this introduces a Gaussian error, but you already subtracted from the Brownian motion by rescaling. Right, so this would hopefully cancel out whatever you are trying to add, and it will be more close to what you wanted it to be. Okay. So SGLD is this, and covariance correction we are proposing is this. But however, this is OBD square computation because you have to compute this matrix with the B points and then multiply it with Gaussian. Can you make it better? Yeah, you can just use a power series approximation. And then, square root of 1 plus 1 minus x is 1 minus x over 2, approximately. And then you can do this approximation. And this can be computed with a slightly intelligent computation. This can be computed in O of BD by. So that is a type. Because it's absorbed into that, but it's of the order eta. You're right. Should probably correct it. Yeah. Thanks for pointing it out. Okay, so this has an O of BD computational complexity. So we want to analyze this and see how it does better and so on and so forth.
Intuition is you're making the noise isometric at every.
Correct. So by approximately isometric, we are expecting how much we might add, so cheaply correct it by rescaling what we have control over. Okay. Okay, to summarize, we had Langevin Monte Carlo, which is no correction and exact gradients, no stochasticization. And there is stochastic gradient, Langevin dynamics, where you have random batches, additional noise. And then you have covariance corrected SGLD, where you rescale the Gaussian noise, the right covariance. So this is a very scary slide. So there are a lot of things going on here. Let me break this down for you. So first is, this is a comparison with prior works. Rajinsky et al. Were the first to analyze SGLD algorithm. They had a lot of assumptions like component-wise smooth, that is each fi of x is smooth, and then it is dissipative. Dissipative, I think, is a very harsh condition. In that if you start going far off, you will start coming back. It's kind of like strong convexity in certain directions, which is much stronger than log-super inequality. And the metric they used was W2, and the convergence rates, the sample complexity was a large polynomial in D divided by epsilon to the 4. And moreover, they needed a very large batch size as well. They needed a poly of D over epsilon. They had an epsilon dependence on the batch size. And this was unstable in the sense that if you stopped at an algorithm at a certain point, they assured that you got a sample. But if you ran it forever, the bounds diverged to infinity. So then Kuan Gu et al. Came and improved this. They could choose a batch size which was independent of epsilon. And they had O tilde D to the 4 over epsilon square. One start means that random Nikodym derivative is bounded between the initial distribution and target distribution. It's very hard to sample such an initial distribution, right? You can just do rejection sampling at that point. So however, the problem is that this is unstable, right? In the sense that this 2 converges to 1 as you take k to infinity, right? There is another line of work by Kinoshita and Suzuki who don't consider SGLD, but variants that use SGLD. They can work with LSI and component smoothness. They also use KL. However, they also get stable guarantees with root n kind of batch sizes. But their sample complexity or computational complexity is d square root n by epsilon square, which is very large. Compared to just this purely polynomial in D, especially when n is very large and D is small. Our analysis for SGLD shows that okay, we have the best of the assumptions, that is LSI smooth but not component smooth, and we just have force moment growth, which can also be removed by using adaptive batch sizes, and we show that we can do this in d to the 1.5 over epsilon square, and a batch size of square root d is sufficient. Moreover, our bounds are stable. Okay, there is adaptive batch sizes which removes this force moment growth condition and actually connects with this variance SGLD, and we get the same kind of complexity. And we have this covariance corrected SGLD which I introduced, which actually further improves the batch size to d to the 1/3, and we can sample this in d to the 1.4 over 3 over epsilon square. So we can see the advantages of using covariance correction.
So in terms of metrics,
Yeah.
Can you just help me compare? Is TV stronger than root KL, for example?
No, root KL is the strongest in this case. If you so normally W2 and KL are not comparable. But when it satisfies a log-Sobolev inequality, there's something called a T2 transportation equality, which implies that you can control W2 with KL, right? So W2 is less than or equal to square root KL up to some constants. Okay, and we also have TV is less than or equal to square root KL by Pritzker's inequality. So convergence in square root KL is the strongest you can have. So yeah, so our work actually considers convergence in square root KL. So yeah, so I won't discuss the interacting particle dynamics in the interest of time. Okay, so the first assumption is that of logarithmic Sobolev inequality. So this seems like a very mysterious inequality. I won't go into the details because it would take a lot of time to explain this. Roughly speaking, this is entropy of a function. This is called the entropy of a function, and RHS is the expectation of grad g squared, right? This is the entropy of a function with respect to this functional here, right? This holds for every function g. So that is why it is called functional inequality. It's a inequality over the space of functions. Okay, we assume smoothness, that is grad f is Lipschitz, L Lipschitz. This is a standard assumption. We assume sub-Gaussian growth in the noise, that is that, okay, this grad f of x comma psi, that is the one component. How is it randomly distributed? If I pick it randomly, then the probability that is greater than t is at most 2 into the minus d square over this factor. That is roughly it is saying that it's subversion with variance being m norm x plus d squared. That is, it grows as mod x squared as x gets infinity. So we allow it to be very, very large when x is very far off from the origin. Okay, and then next one is that the moment growth condition. So for some p, I'm not saying for every p, I'm just saying for some p, which I'll specify later, p equals 4 or p equals 6, the iterates are bounded. The qth moment of the iterates are bounded by d to the p over 2. What does this mean? This means that, okay, if I have p equals 4, fourth moment of these iterates are bounded by d square. Why does this make sense? This means that each coordinate is of the order 1. If that happens roughly, then this is satisfied, right? So this is the reason we use this. We use this assumption. In fact, this is a very mild technical assumption, and this is weaker than dissipativity, which is used in the previous works. And it is also not essential, we can use adaptive batch sizes, which will adapt to how large x is, and then we can also remove this assumption. So it's not a big deal.
How do you, like, just to sort of get my head around, like, logs overlay, right? How do you, for pi star, like, is there a way to analytically test it? I'm wondering, like, in practice, is it just like...
It's very hard to establish logs overlay.
You just, on faith, assume it's there and march on.
So basically you're saying, okay, there's this huge set of the non-log concave functions which you can sample.
Is some Gaussian group assumption?
No, they actually have much harsher conditions in that they assume almost sure bounded.
Some Gaussian is just that it concentrates.
It concentrates on this. Yeah, but you can't relax this much further. Okay, so the first theorem we have is the stable last iterate convergence for SGLD. We have a lot of theorems in our paper under various functional inequality assumptions. I'll only mention a fraction of those. So the first one is last iterate stable convergence of SGLD. So suppose we assume L smoothness, which I just described, and you have subversion noise growth and logarithmic overlay inequalities and fourth moment condition. That is, the fourth moment of the iterations is of the order d squared. Okay, so then if you pick eta is less than or equal to lambda LSI over 6L squared, then we have KL between xk plus 1 to pi star is of this form. The first term shows how the KL how it forgets the memory of the initial iteration. That is, it decays the KL of the initial iteration to this exponentially fast. And the next term is second term is the bias by discretizing a stochastic differential equation. And the third part is eta d square over lambda LSI times d square, which is actually the noise introduced by us by using stochastic approximation. This is of the order 1 over b square for a very specific reason, and it is because of the CLT. Right? It is previous works actually get 1 over b or even O of 1 kind of thing, right? So which is not very nice, but we actually get 1 over b squared, which is the optimal thing to do here. Okay. So okay, so let's unpack this bound and see how it implies a sample complexity.
You're not using adaptive step size.
It just adaptive step sizes I won't discuss here. What you do is you take x, right? You take norm x to be the batch size, max of norm x, comma n. So something like that, and then it just works. It cancels out the bad factors of extra moments you need.
And when you say law of x hat k, is that known?
The distribution. Okay, it's you can initialize it to whatever you want, right? You can initialize it to, for instance, to a right Gaussian. Then you can ensure that this is polynomial indeed. So what appears in the complexity will be polylog indeed. So okay, so let's say eta we take it to be epsilon over d, and then batch size to be of the order square root d, so that these two terms become equal, and then iterations k to be d over epsilon. Okay, so then we can assure that the KL between the last iterate of this is of the order epsilon. Okay, so what is the oracle complexity? That is the number of steps we took, k times d, which is times d, which is the batch size, so which is d to the 1.5 over epsilon, like I promised. So we achieve this, and this is the best known complexity for Langevin under very standard assumptions. Okay, let's.
What's the optimal batch size?
I don't know if it's optimal, but this implies that. Okay, so what happens is if I increase it much beyond square root d, this term starts dominating, so it actually won't decrease any diminishing rate.
Can pi star be actually just full concentration?
No, it can't satisfy. No, it's e to the minus f, right? It has to be distributed. It's no function. It has a density with respect to the Lagrange medium.
This, when like instead of LSI, you sort of say apply the same analysis to log concave limit, right?
If it's strongly log concave, yes. But log concave, I think you'll have to use different methods. We haven't checked that out. We actually extend to Poincare inequalities. I think they are satisfied by log concave. So, right, that's KLS, right? So if you have Poincare, we also have it, but you have to use different techniques.
So here that exponential term e power minus lambda is it's turning out to be constant.
Which one? This one?
Yeah. Like
No, it's O tilde, right?
Oh.
Yeah. So yeah, that's enough to cancel it out. So if you just had eta tending to 0, if you look at the stochastic differential equation, you would have only this exact stochastic differential equation. You won't have the extra.
So for logarithmic batch sizes, can we get any k where it converges?
Logarithmic batch sizes, then you have to set eta to be very, very small. Right? I mean, this holds for all batch sizes. If you pick this to be that, then you get sample complexity, total oracle complexity will be higher. Or the upper bound suggests that it is higher. I won't say that it is higher, but the analysis is weak.
So just trying to understand KL again, you're saying that eventually after time k plus 1, your iterate xk plus 1 lies within pi star with the concentrates within the distance.
It's more like, okay, consider the space of probability distributions. So that itself has a geometry. It could be Wasserstein geometry or total variation distance geometry or the geometry given by KL divergence. So you can write a KL ball. KL is not a metric, it's a pseudo-metric, let's say. Not even pseudo-metric, but metric-like thing, divergence. Yeah. So, so there is a geometry given by that and it lies within the ball of that. So this is actually a gradient descent in the space of metrics. So it's actually gradient descent over K. Yeah, so moving on, let me give you a short proof sketch. So how we proceed with this is by actually going back to continuous time stochastic differential equations. So even if you have discretization, you can just do linear interpolation like this. Like you start with x naught, which is a linear interpolation process, and then write this stochastic differential equation. So instead of taking grad f of xt, I just truncate it to grad f of xk eta, that is previous time step. At integer times, this will actually be your actual iterations, but at non-integer times, it's a linear interpolation between. Okay, so let's call mu t to be the distribution of xt, and we know that mu of k eta is actually the law of iterate xk. Okay, so we can compare it to continuous time Langevin dynamics. So here xt bar, let's denote it by the continuous time Langevin dynamics. Okay, here there is no, this is actually x bar t and there is no n. Okay, we want to compare this to this. Bakary-Emery theory shows that rate of change of KL divergence is minus half of Fisher divergence. Fisher divergence is another local divergence kind of thing. I won't go too much into detail. It's almost surely positive. Let me just tell you that it's a functional over the space of measures. Okay, so we saw that if you had the exact stochastic differential equation, this is how the KL divergence between mu t bar and pi star revolves. Okay, but we have an approximation of this. Now, how does this work? Okay, so we modify the proof of Bibisono and Mempala, but for the LMC and show that, okay, so this has additional terms. So of course, okay, this term appears, but there's a discretization error, which is f of xt minus f of xk eta for using stale values of xt. And there is a stochastic gradient error, that is expectation of n given xk eta comma xt whole square. So we have to add these two errors. Yes, so the discretization error is actually easy to control. It's a Lipschitz function and so on, and it is actually turns out to be 1/4 Fisher divergence plus eta d. It's not very hard to show. However, now we are actually left to control the stochastic gradient error. So this is the main part. So if we have that CLT says that if log of n given xk eta is sigma of k eta, right? So then what if it was exactly Gaussian? Then we can use the properties of Gaussians to show that there's a conditional. You can know the exact conditional distribution of Gaussians, and we can show that this holds. This property holds. Expectation n given xk eta x t is less than or equal to eta trace of sigma of xk squared by b squared. That is where by this b squared comes up because of this Gaussian approximation. Okay, and then we know that trace of sigma xk squared is less than or equal to d squared by noise growth condition and the fourth moment condition. And then plugging that in, you get eta d square over b square. This is the thing we got. Okay. Okay. So, but however, this is not exactly Gaussian. This is actually an IID average of zero mean random vectors. So the technical challenge is to actually consider non-Gaussian things and do a Gaussian approximation in a non-asymptotic way. We show that a CLT style result, conditional CLT style result, actually can give us this up to the same result. And going back to this EVI, this kind of descent lemmas are called EVIs, this kind of differential equations. D by dt of KL between mu t to pi star actually evolves like this. Okay, so now we apply the logarithmic stability algorithm.
Eta is small, is it k eta?
Eta is small.
Is k eta? You are assuming p lies between k eta and k plus 1.
Yeah.
So is k eta much more?
No, it could be constant. Oh, constant, right? But the interval between them should be small, so that the. Okay. So we have this descent lemma, and log-Sobolev inequality shows that this is the main use of log-Sobolev inequality. This is kind of it follows from the definition of log-Sobolev inequality. If you put G to be the Radon-Nikodym derivative of mu t and pi star, this is what comes up. That is, Fisher divergence between mu to pi star is lower bounded by 2 LSI times KL of mu to pi star. Okay, so therefore we have that. KL has this Grunwald lemma kind of thing. So there's this exponential decay plus this constant approximation and estimation error, right? So if you apply Grunwald's lemma and integrate this out, we get this statement of the previous theorem. That is the sample complexity which we desired. So you can see that this eta d is there and eta square d square over b square is also in the statement of the theorem. Okay. So let's look at the analysis of covariance corrected stochastic gradient longitudinal dynamics and LMC. So here we can't write EVI so easily. We use a slightly different proof technique, and here the CLT actually shows up in a much more prominent way. Okay, let's say that x hat 1 to k is the iterates of CCSGLD, and x1 to k are the iterates of Langevin Monte Carlo. Right? We have the same initialization and same step size. Right, we want to show that the trajectory of first thing and the trajectory of the second thing, they are almost indistinguishable, right? Okay, so we'll assume that this expectation xk hat to the power 6 is of the order d cube. It corresponds to each iterate being O of 1, each dimension being O of 1, and we'll assume this almost short bound on the stochastic gradient noise, but it can grow with respect to x, but it's still bounded. Then what we show is that KL between the trajectory of CCSGLD and that of LMC is at most eta square d square k over b cube. So in the previous result, we had a b square dependence. Now we have 1 over b cube dependence, right, with the error. So this is because of the covariance correction. Okay, so now we didn't assume any functional inequalities here. We did not assume LSI or anything. But however, on top of this, if we assume LSI, and we pick eta of the order, it should be epsilon over d. Yeah, it should be epsilon square over d, and b of the order d to the 1/3 instead of square root d, and k of the order d over epsilon square. Then TV between log of xk hat to pi star is of the order epsilon. So this gives us a sample complexity of d to the 4/3 over epsilon squared, which is an improvement over square root d over epsilon. Okay, so let's look at some rough proof ideas. You have the CLT here, and you have covariance corrected SGLD, which we have here plus noise plus correction. Okay. So LMC, actually the output of LMC, no, this is not SGLD, this has to be LMC. Output of LMC is actually a random function. There's a random function representation. It is actually a function of these input noises. So if you tell me, if you are an oracle and tell me what noise you're going to use, I can give you a function hk and apply that function on this epsilon 0 to k and output this xk plus 1. And how do you output? You run this. So it is a random function of these random variables. Okay. So now we can rearrange these things. You add the noise here and absorb it and define zk, z hat. That is, z hat is 1 I minus eta sigma k hat over 4 epsilon k plus this nk, this noise. Okay. I think there are factors of eta missing here. That's a typo. Okay. So a CCSGLD is equivalent to running the algorithm instead of with epsilons, we run it with z hats. The functional form remains the same. If I tell you z hats, you can run this and you get x hat onto k plus 1. So this satisfies the same random function representation. These hk's are the same. Okay. So now we know that law of x naught is equal to law of x naught hat. So we just apply the data processing inequality. So you have this function hk applied on epsilon 0 to k, and function hk applied on z hat 0 to k. So the KL between x hat to x is at most the KL between these driving noises, that is z hat to epsilon k. Epsilon k we know is Gaussian, so we want to bound the KL between z hat k given fk, that is conditioned on the past. What is the law of zk and how close it is to Gaussian? So this is literally a entropic CLT in relative entropy, that is KL. Okay, we want to prove this entropic central limit theorem. Okay. We are just rewriting what we had in the previous slide. Okay, so we will decompose this KL term into covariance mismatch and Wasserstein CLT. So firstly, we made an approximation or an estimation of the covariance. We didn't use the exact estimate. So that will give you T co, the first error term. And the second one is because we are not using exact Gaussians. We are using sum of IID things. So that will give you a CLT error term from the CLT. Okay. So here T co is of the order KL between. Okay, this is a triangle inequality, but we can rigorously prove this using functional inequalities and properties of Gaussians. Okay, it is there will be some constants which show up, so we can make this hope. So like I said, the first one models the error that we are not actually using the exact covariance, but we are using sigma k hat. Okay, this is easy to bound using estimate. What is the estimator you're using for sigma k hat? And the second one is that, okay, suppose you had the exact covariance. What is the error because you're not using exact Gaussian noises? So this is actually a Wasserstein CLT. That is CLT in Wasserstein 2 distance. And then we use the properties of covariance estimators to show that this T covariance is of the order eta square d square over b cube plus eta cube d cube over b cube. This is the gain we actually obtain because we are estimating this. And then TCLT, this is a non-trivial aspect to prove. We have to actually go through Wasserstein CLT and then modify it a bit and prove this non-asymptotic version of the central limit theorem, which shows that the Wasserstein 2 distance between these two is of the order eta cube d over b to the 4. So it's a much smaller order term of the order 1 over b to the 4 times d cube. Right. So this follows from by actually adapting Alexei's famous work on Wasserstein 2 CLTs. And then moment growth condition on norm x cube implies that this is of the order eta cube d to the 4 over b to the 4, and this is a lower order term compared to the covariance fraction. Covariance. And putting all of this together, we know that the KL divergence between using LMC versus using covariance corrected SGLD is of the order eta square d square k over b cube, and this completes the proof. And here we are actually using a Bayesian type CLD to prove an entropic CLD. Conclude, yeah.
Finally, we are bounding the total variation distance.
Right. So total variation is always bounded by square root here. Principal inequality. So to conclude, we analyzed random batch approximations of stochastic gradient based sampling algorithms. Okay, the error due to stochastic approximation we saw was nearly Gaussian due to the CLT. Okay, this can be hidden inside the diffusion term. That is Gaussian. If you add a small Gaussian looking error to a large Gaussian error, it is indistinguishable from the large Gaussian error. So that is the thing we are using. So we added to the diffusion term whose increments are exactly Gaussian when we hid this noise there. And this actually doing this in a smart way gives us state-of-the-art convergence analysis and algorithmic improvement techniques. That is by using covariance direction. And this has a rich range of future directions, and that is we can try to analyze this in stronger metrics like Renier divergences, which are stronger than KL divergences. We can consider Hamilton Monte Carlo and extend it in that direction. And that shouldn't be too hard, I think, but yeah. So using some of the concepts introduced here, and then yeah, so these are some of the future directions we are considering. And I think one more is that can we come up with better discretizations so that we can use much larger batch sizes and still expect some improvements. So here it was literally not useful to make batch size larger than 2t. You would stop getting any improvements. But if you can reduce the bias error in Langevin Monte Carlo itself, maybe you can pick much larger things of the batch size and get a very good approximation. So that's something we are looking at in the future. I think this is the end of the talk. I can take any questions.
Okay, so when you spoke about CLT over measures, can you for CLT you need large number of samples?
Yeah.
So for you, that large number of samples in the previous slide is K.
No, it is B. So CLT, of course, there's an asymptotic CLT and a non-asymptotic CLT. Asymptotic CLT is a classical Kolmogorov CLT, right, where you have n tends to infinity and you don't specify the rates. There's a second type CLT called Bayesian CLTs, where it holds for every n. So you get a distance measure between your distribution and your Gaussian, and you show that, okay, as a function of n, how it decays. For instance, Bayesian shows that in Kolmogorov's Smirnov distance, you get a square root of 1 over square root n, where if you have n samples, or if you have b samples, it's 1 over root b. Okay, and Alex Zeiss Wasserstein's CLT work shows that it is of the order 1 over b. However, we have a much more better condition where you have a large exactly Gaussian noise with a very small empirical sum. So here actually you get 1 over b to the 4 rates for the Bayesian rate. So it's exactly b. It works for every.
And I'm guessing like CLT over measures. This
CLT over measures.
Yeah, no, I mean the specific form that talking about the previous slide. Can it be used for other online sampling?
Yeah, I'm trying to go back to the slide. Yeah, here, right? Yeah, so actually I was actually trying to look at that, but I didn't have the bandwidth. So this kind of thing. For instance, if you are using UCB, right? If you have large enough number of samples, it's an empirical sum. You can write a martingale CLT there. So you can actually set the constant C for the upper confidence. Log n whatever with this Gaussian kind of actually do that. But I don't know if you're working with it might be something. No, not even Gaussians. Like if you have literally third moment or fourth moment, write a Bayesian CLT for it. As long as you have empirical.
Like you see without it, as is vanilla UCB is tight even for one.
Yeah, so it's like up to constants, right? Not okay. So there is a UCB index you compute. It's C times square root log n over n. If you deploy it. So maybe this can give you a way to pick C. So if you're aware of Sandeep Juneja's work, so there they actually choose all of these constants, etc. Exactly.
So it's a like okay, maybe the constants, let's not call them constants, those parameters can be fine-tuned, but otherwise
Otherwise,
it's tight. As tight as it is. Yeah.
If you want to do even better compared to that,
Like the typical uninspired question, what are lower bounds?
This one, I haven't gotten around to doing it. Even LMC, right? You don't know what are the lower bounds. There are some works I haven't read them yet, but yeah. It's not very well explored yet.
Any other questions? Not less. Thanks.